So let's try that again with the graph. I'll have a parabola with a vertex of -3, -5. And we already said it is a function. We said, yes, it's a function because there's nowhere along there, if we move that vertical line, there's nowhere that's going to ever cross that twice. So yes, it is a function. So then let's talk about the domain. Remember, the domain is on the x-axis. The domain here, there's any value of x that I put in here, I will find a value of y. So the domain here is all real numbers, going from -infinity to +infinity. My range is a little trickier. Here, because of the positioning of the vertex, the range, the y values, remember, that's what the range is my y values, will never be less than -5. Now it equals -5, but never less than it. So it goes from -5, notice the square bracket, so it includes the -5, up to infinity. Because it will go up here as far as it wants to. It can go as high as it wants to for value. Often we are concerned about describing functions. And one of the things that is most telling for us for describing functions is increasing or decreasing. And what it's basically telling us to do is as the values of the domain get larger, what is happening to the value of the range? Well, if the values of the domain get larger, if the values of the range are getting larger as well, then it's increasing. The values of the domain are getting smaller, then it's decreasing. Now it can be absolutely increasing, or it can be just on an interval locally. If I look at a graph of this function here, that's neither increasing or decreasing. But if I look at it from the interval from here to here, on that interval, it is definitely increasing. If I take a different interval from here to here, on that interval, it's definitely decreasing. So whether it is getting larger or smaller over a certain portion of that domain is one of the things that describe their functions. The other big thing is called a maxima. Or a minima. Now these are pretty common sense from the prefix. Max, of course, means largest. Min means smallest. And once again, it can be absolute or it can be local. If I have a graph, let's go back to my parabola. with a vertex at -3, -5, there is an absolute minima. That is the smallest value of the range of that function. So for the domain value of -3, we get the absolute minimum value, minima, of the range, in this case of -5. But it could be a relative or sometimes called a local maximum or minimum. Again, looking at a graph, it looks something like this. Let's say that that point is -1, 9. And let's do this point here. We'll call it 15, -12. Over this range, in fact, I could expand that a little bit. I can go all the way out to here. Over that range in the brown, this is a relative or local maxima. It is the largest value of the range of that function over that section of the domain. This is a relative minima. It is the smallest value of the domain or the range of that function over that section, portion of the domain. A little bit more complex concept that describes our functions is symmetry. Now, the one that we've been using here, our parabola, with that vertex at -3, -5 still, it has symmetry. If I draw a line here, that's the line x equals -3. It is symmetrical about that line. And the most common symmetry that we deal with is symmetry about a line. So, and all that means is if we take that line, x equals -3, if we take one side of the graph and fold it at that line, that first side will lay exactly on top of the other side, on the other side of the line. Now, in algebra, we can be symmetrical about a lot of different things. But typically, we're most concerned about symmetry about some of the landmarks on our graph. So we talked about symmetry about the y-axis is a big one. We're symmetrical with respect to the y-axis. What that means, of course, is what's on the left side of the y-axis, whatever it is going to fold over exactly onto the right side of the y-axis. Algebraically, what that means is if you substitute -x for x, you get an equivalent equation. In function notation, what that's telling us is f of -x is equivalent to f of x. Well, let's take a look at a function that is symmetrical about the y-axis. Let's check to see if If we have, we might have y equals x squared minus 8. To check to see if that is symmetrical about the y-axis, we're going to substitute negative x in for x. So instead of y equals x squared, y equals negative x squared minus 8. Well, negative x squared is just x squared minus 8. Those are equivalent equations. So yes, that is symmetrical with respect to the y-axis. We might have something that's symmetrical with respect to or about the x-axis. Again, that means if we fold this graph with the line of the fold being on the x-axis, what is below the axis will exactly fold on top and match up with what's above the axis. Similar to what we had for the symmetry about the y-axis, here we can substitute negative y for y and get an equivalent equation. So I might have the a relation, I should say, x equals, should put it like this, y squared equals x minus 2. If I substitute negative y for y, well, once again, put negative y in there for y. Well, negative y squared is just y squared. So again, I have an equivalent equation. Now notice I caught myself, I almost said function, and I corrected myself to be a relation. This is not a function. Relations that are symmetrical about the x-axis cannot be functions, because by definition, there has to be a point below the x-axis and another one above the x-axis for each value on the x-axis. For each value of the domain, there would have to be 2 points, 2 values of the range. So symmetrical about the x-axis cannot be a function. However, symmetrical about the y-axis can be a function. There's a third type of symmetry that deals with standard positions of the graph. As you saw above, we can pick any line on the graph and we can be symmetrical about that line. But it's symmetrical with respect to the origin. To be symmetrical with respect to the origin, what does that mean? Well, what that means is you literally reflect around the center of the graph. If there's a point here, it has a corresponding point exactly on the opposite side of the graph. If there's a point here, again, you go through the origin and continue going the same distance the other side. There's a corresponding point over there. Algebraically, how that is accomplished is if I substitute x in, negative x in for x, I get a function that is -1 times the function. Often it's written as just negative f of x, like this. Let's talk about even and odd functions. We mentioned symmetry around the x-axis would create a relation that is not a function. So we have symmetry about the y-axis and symmetry about the origin. An even function is symmetrical, as symmetry about the y-axis. So again, that is, I can replace x with negative x, I'm going to get the exact same equation, exact same function. An odd function has symmetry about the origin. Why do the terms even and odd make sense here? If I have a function, y equals 3x to the fourth minus 5. If I were to graph that, now I could make the table and graph it, but I'm just going to use my calculator here to do this. But I say 3x to the fourth minus 5. So 3x to the fourth minus 5. There's my equation. If I graph this, I get a graph that looks like that. Notice that is symmetrical about the y-axis. If I do y equals x to the fifth, well, let's just do y equals 4x to the fifth. So I'm going to clear this out. When I graph that, you'll see what I get. I'll draw it out a little bit larger here for you. It looks something like this. That is symmetrical about the origin. If I pick any point on the graph, like right here, I go to the origin and I go the equidistant on the other side, there's another point that's still on the graph. Notice the powers in the equations. That's an even power of the variable. That's an odd power of the variable. So those are where those terms of even function and odd function come from, is because the powers on the variables that produce that kind of symmetry. Well, there is another slightly more complex type of function that we want to deal with. And we drew a picture of it earlier, but we didn't talk about it. And it is called a piecewise function. Some things just can't be described with a single equation. So what we do is we break the function down into pieces, and we describe each piece with an equation. You know, for example, we might have a function that's described like this. So that big squiggly bracket there is telling us that we're going to have multiple definitions for this function. So it might be two x squared minus 4 for x less than or equal to 0, and 3x minus 4 for x greater than 0. A piecewise function, a piecewise relation, I should say, is a function on two conditions. Condition 1, each is a function separately. Two x minus 4 would be a function all on its own. We can actually restrict it further, even if it isn't a function on its whole domain. If we restrict its domain to x minus, or x is less than or equal to 0, would it be a function on that domain? And it definitely is. But 2x minus 4 is a function on its full domain from negative infinity to positive infinity. 3x minus 4 is also a function from negative infinity to positive infinity. So we don't even have to worry about the restriction on its domain. Second, if the domains of the individual functions don't overlap. Note, this one goes up to and includes 0. This one starts at 0 without including it and goes up from there. So the domains do not overlap. And those two functions on those defined domains combine to make one single piecewise function, which can be graphed. Two x squared minus 4 looks something like this. But no, we only want it to go up to, oops, wrong side erase there. I only want it to go up to x is less than or equal to 0. So I only want it to go up to 0. So that side isn't needed. And then the second function, 3x minus 4. Well, that looks like that. But again, we only want that to go from greater than or equal to 0. So not even at 0, but at all values above 0. So I don't need this piece here. So that, those two pieces of those two functions put together, the part of a parabola there and the straight line here, make that piecewise function. Now, sometimes we use piecewise functions to define functions that have holes in their domain. For example, if I look at a rational function, f of x equals 3x minus 2 over x plus 5. It may not appear to be, but there is a hole in the domain. There are values that are impossible. There are two things that we cannot do. One, this is the most common ones, we cannot divide by 0. And two, as long as we're working in the real numbers, we cannot take the square root of a negative. So when I look at this function here, because it is a rational function, we are dividing by an expression that has a variable in it. You know, if it were just over a number, we wouldn't have any issues. But we have to make sure that that denominator does not equal 0. So x plus 5 cannot equal 0. Well, where would it equal 0? Well, we solve it for 0. If I subtracted 5 from both sides, that's saying x cannot equal -5. So when I am defining this function here, I can say f of x equals 3x minus 2 over x plus 5, but I have to define the domain. I would say it's that function over the domain. We go from -infinity to -5. Notice the round bracket saying that -5 is not included. Union with -5 to +infinity. So that's just saying that all values except for the -5 are in the domain of that function. We might have f of x is equal to the positive square root of x plus 7. I had to have the positive in here because the square root of x plus 7, there's a positive value and there's also a negative value. If I include the negative value, that's not a function because that vertical line would cross it twice. So if we only include the positive square root, then it is a function. However, this is a root and we cannot take the square root of a negative number. So the domain for this, the x plus 7 has to be greater than, can it be equal to 0? Sure, the square root of 0 would just be 0. So we solve that to define the domain by subtracting 7. X has to be greater than or equal to -7. There is our domain. Now from the graphs of these, we can define often the range. Like on this one, pretty easy from the graph to define that that range is from 0, should be a square bracket because the square root of 0 does equal 0, so 0 is included in the range, to +infinity. Because as my x values get larger, this will slowly get larger up to infinity. So the course is entitled Algebra for Calculus, which basically means we are giving you the algebra skills to get you ready for calculus. So one of the bridge skills that bridges algebra to calculus is something called a difference quotient. A difference quotient is just saying, let's describe how the function behaves over a short range. Now, once you get into calculus, calculus is going to talk about, well, what happens is that range gets smaller and smaller and smaller and decreases down to essentially 0. Well, we're not going to get quite that small. We're just going to go to a limiting number, which we're going to say is h. And we're just going to define h to be a really small amount. We can make it slightly smaller, slightly larger as we want to. And again, in calculus, the object is to make it small enough so it's what they call infinitely small or infinitesimally small to make it basically 0. But the difference quotient is simply f of x plus h minus f of x divided by h. So it's measuring, but technically what it's measuring is the change in the function over that range of h. And calculus, as I said, as the h gets infinitely small, it's going to be an instantaneous rate of change. Something you're going to refer to as a derivative when you get to that point. So if f of x equals 2x minus 7, let's find the difference quotient. Well, first of all, we're going to define f of x plus h. That's going to be 2, and instead of x, we're going to put in x plus h minus 7. So that's 2x plus 2h minus 7. So the difference quotient is f of x plus h, which is the 2x minus or plus 2h minus 7, minus f of x, which is 2x minus 7, over h. We have to subtract up here. You remember how to subtract? We're going to change the sign. We're going to change this to plus. We're going to change the sign of every term inside the parentheses, then remove the parentheses. Now we can combine like terms. 2x and negative 2x cancel out. There's nothing to combine with the 2h. Negative 7 and positive 7 cancel out. So on top, once we subtract those functions, we're left with simply 2h. Divided by h, well, the h's cancel out, we get 2. So the difference quotient for f of x equals 2x minus 7 is simply 2. If you remember when we talked about linear equations, 2 is what's called the slope of that equation. That is the rate of change of that equation. It's a linear equation. It has a constant rate of change. It'll always be 2 as its rate of change. Some higher order equations, however, have a slope that changes according to its value. So let's look at f of x equals x squared minus 2x plus 5. To find its difference quotient, we're going to first have to find f of x plus h. So that'll be x plus h squared minus 2x plus h plus 5. We've looked at perfect square trinomials. So x plus h squared is x squared. X times h is xh times 2 is 2. We go hx plus then h squared. Again, that's just taking x plus h times x plus h and foiling it out to get that. We've got the negative 2 times x plus h, that's minus 2x and minus 2h, and then the plus 5. That is f of x plus h. So now we have to find the difference quotient. So f of x plus h is x squared plus 2hx plus h squared minus 2x minus 2h plus 5 minus f of x. So minus x squared minus 2x plus 5. And of course, all over h. So as we subtract here again, you got to change that to plus and change the sign of everything inside here. X squared and negative x squared cancel out. Negative 2x, positive 2x cancel out. 5 and negative 5 cancel out. So what we're left with over here is 2hx plus h squared minus 2h, still all over h. If I divide by the h, 2hx divided by h is just 2x, plus h squared divided by h is just h, negative 2h divided by h is just negative 2. There's our difference quotient, 2x plus h minus 2. Now again, in calculus, if you're looking for the rate of change, you're letting h go to 0, so that h would disappear. The rate of change would just be 2x minus 2. So that describes the slope of the graph as a function of what the point it is in the domain of that graph. Any questions? I'm going to have you guys try a simple difference quotient here quick. So find the difference quotient. For f of x equals 2x squared minus 5. I'll give you a couple minutes to find that. So we're going to subtract. I'm going to put this plus and then change the signs in here. 2x squared and 2x squared cancel out. Or 2x squared and negative 2x squared cancel out. Negative 5 and positive 5 cancel out. So we have 4xh plus 2h squared over h. We divide by h. 4xh divided by h is 4x. 2h squared divided by h is 2h. So 4x plus 2h. Any questions there? One last example to review some of our stuff for today, and then it's going to be time for me to have to get going here. We're going to look at a piecewise function. We're going to find the domain and range of the piecewise function. F of x equals 0 if x is less than negative 3, equals negative x if negative 3 is less than or equal to x, or less than 0, and it equals x squared minus 1 if x is greater than or equal to 0. To me, it's often easier to graph these out to define the domain and range. So let's do that. X equals 0. Sorry, f of x equals 0 if x is less than negative 3. So remember, f of x is really y equals 0. if x is less than -3. That's just a horizontal line here. Goes off in that direction, but it ends at -3. And it's going to be an open dot there because it's less than, or strictly less than. Negative x from -3 to 0. So if x is -3, negative x would be +3. -2, negative x would be +2, and so on, down to 0. So that's a solid dot there because it's or equal to on the -3. Down to 0 would be an open dot because it's strictly less than there. And then x squared minus 1 for x greater than or equal to 0. X squared minus 1, if you list the points, it's going to form a parabola like this. So I'm going to give you about 20 seconds here looking at that graph. Try to tell me what you think the domain and range are. Use interval notation. So when I check my domain, two things I check. I check the infinities. Does it go off to negative infinity? In this case, does this go off to negative infinity? Yes, it does. Does it go off to positive infinity? It does. This can keep going. It's going to get steeper, but it will slowly go off to positive infinity on the x-axis. So the second thing that I need to check for the range, or sorry, for the domain is, are there any holes in the domain? Well, that's an open dot, but there's a solid dot here that takes up that spot. Same here, there's an open dot, but there's a solid dot here that fills that in. There are no holes in the domain as we go across the graph. So this domain is truly negative infinity to positive infinity. The range is a little trickier. This range does have limits. Remember, range is your x values going up or down. The smallest this ever gets is -1. Does it include the -1 or not? Well, yes, x squared minus 1, x is greater than or equal to 0. It does include the -1, so I have to put the square bracket there. And then, of course, we can see here, this is going to shoot off to positive infinity in the y direction. So it goes from -1 to infinity, like that. Okay, so remember, you do have homework due from last class. That's homework 2A. It's due from last class, which will be due tomorrow, Tuesday. And then from today, our new material is homework 2B, which is going to be due on Thursday. And those two homework assignments are what's going to make up the quiz 2. Quiz 2 should be open, I believe, starting tomorrow. It'll be due on Friday. Any questions? Okay, you guys have a great day. We'll see you all on Wednesday.